Okay, so we're going to start with particle on a ring. I think last time we finished with harmonic oscillator. Yes? Yes. Okay. So for this one, we're going to imagine that we have some sort of a ring of fixed distance. So if we have a particle going around in a ring, we can think of that as, now this is more convenient. We have along the x, y, and z axes, the ring is going to be rotating around the x and y, so there's really no z component to its rotation. Right? So essentially, we're trying to figure out this particle moving not in 3 dimensions, not in 1, but in 2, similar to our particle on a sheet that you guys did as part of homework 2. But now instead of taking up like a square, it's going to be rotating around a circle. Okay? And then we're going to say that the circle, to simplify things, we're going to say that it has a fixed radius. Right? So it's only going around. It's not, able to change the distance to the center. Okay, so we would start out as having a wave function. So we start out where we always start out, which is Hamiltonian wave function. So we have it currently in the x and y axes. That would be equal to our energy xy axis, right? The reason it's x and y is because it's rotating around the x and y axes, so there should be some component of the x, some component of the y, and Hamiltonian because, that's what we do. So if we write this out, that would be minus h bar squared over 2m times partial derivative, or the second partial derivative with respect to x, plus second partial derivative with respect to y, applied to our wave function, and that's our energy times our wave function. So we, at this point, would have to be able to solve it in terms of 2 different variables, right? So that sort of complicates matters. The x and y, we could set x as being equal to r. Let's see, if that's our r, and then looking down at it from the top, this is our x, that's our y, then it would be r cosine, and then we're going to say that the going around here, we're going to be using, what do I have? Phi. Let's make that a little better. So the angle that we're going to be using is phi as opposed to theta, which we have been using for other stuff. Okay. So we could say r cosine phi and y is equal to r sine phi. So we can actually express this in terms of, instead of x and y, we can express it in terms of r and phi. And then if we say that r is constant, then instead of having this in terms of 2 equations, or 2 unknowns, we can have it in terms of just 1. Right? So we're going to switch from going in Cartesian coordinates to polar coordinates. And the reason we're doing that is we can go from a 2-variable problem to a 1-variable problem. And that makes life a heck of a lot easier. When we do that, however, let's see, this part here where we're taking the derivatives, switching this particular thing into polar coordinates is equal, oh, it's up on the board, 1 over, if we're keeping R constant, so let dr equal 0, right? Constant R. That's, no, sorry, yeah, del phi squared. So this is how we're going to switch from working in our Cartesian to working in our polar coordinates, right? So this part here, our Hamiltonian, then becomes minus a bar squared over 2m. We're now going to do the 1 over r squared, and then del squared del phi squared, second derivative with respect to phi of our wave equation, and instead of being in terms of x and y, we swapped to polar coordinates. R is being held constant, so it's just in terms of phi. Okay, equals e phi of theta. Now from physics, this value here, 2m r squared, well, at least the m r squared should hopefully look somewhat familiar. M r squared is your moment of inertia from going around right. It's sort of the equivalent of mass for a rotating body. So there are a couple terms that are related. You know, when we're swapping from going polar coordinates, or sorry, going from Cartesian coordinates to polar coordinates, there's this one, which is akin to mass. Then there is our angular velocity, which is somewhat, in terms of the equations for like kinetic energy, that's kind of the equivalent of velocity for something going in a line. We have our angular momentum, which is sort of the equivalent of our regular momentum. And then in both cases we have kinetic energy. Okay, so this is polar. That one's Cartesian, or moving along the x, y, and z plane. Okay, we're going to be using some of these today, and so I just want you to, in the back of your mind, if I have I, you can think of that. The way it works in something that's rotating is kind of like the mass, right? This W is kind of like velocity. J is kind of like our momentum, right? So when we're talking about kinetic energy, kinetic, we've been previously saying that that's our momentum squared over 2m. So if we're talking about something in our polar coordinates, this would be, we could write this as I 1/2 1/2 I W squared, right? So 1/2, it's kind of like 1/2 mv squared, except we're using our polar type values. And so instead of being momentum over mass, it is the angular momentum over, angular momentum squared over 2 times our equivalent thing for mass. Right, so we can do kinetic energy going around a ring using similar equations to what we had if it's going in a straight line, just using our polar equivalents to our linear equivalents. Right? We end up with, they might not necessarily look the same, but if you know that J here means virtually the same thing as P, then it starts to make sense that it's mapping out in a 1-to-1 ratio. Okay, so we have this part here, 2mr squared. We can actually rewrite this as minus h bar squared over 2I, and then right, and then now instead of having mass, it's more in our rotational units. Just another way of pulling everything together to be more in terms of rotation. Okay, so the wave function that we're going to be using is one that's similar to what we've seen before. That's going to be, so the normalized wave function. We're not going to go through all the process of normalizing. Our normalization constant is the square root of 1 over 2 pi. And then our wave equation is going to be E to the I m sub L phi. In the Atkins book, it actually steps through the entire derivation of how you get to this. And so we're not actually going to go through it. I'm more interested in you being able to apply these than being able to derive them. But if you want to see the derivation, it's in the chapter in the book. Okay, so what we want to do, some of the things that I am interested in, is your ability to test, is this a valid wave function? And then what are some of, what's the expectation values, things like that. Okay, so if we're imagining a wave going around a ring, one of the things about our wave functions, if you remember back to the limitations on wave functions, is they need to be single valued. So at any point around the ring, there should only be one value. Okay. Now, because it's traveling around the ring, it's going to come back and travel around the ring again, and keep traveling. So each time that it comes around, it needs to line up with where it was the first time around. Okay, so what that means is that our value, as we go around the ring, has to be the same as the next time around the ring, right? So going around the ring is 2 pi radians. So if we go, quarter radian the first time around, we go pi over 2 plus another quarter radian, we're at the same spot, right? So this value here should be the same as that value there. If it's not, right, so the next slide has sort of this idea where if they don't line up around the second circuit, you're going to end up having your wave equation not lining up. So here you'd end up having at, well, I guess about a quarter radian, you'd have 2 different possible values for your wave function, which we can't have. Right? Wave functions have to be single valued. So we can't have that. What we need is that each one of them line up. So the limitation on that is that this has to be true. So we need to check that for this wave equation, that holds true. Okay. More fundamentally, however, we got to make sure that when we plug this into our equation here, we get back our wave equation times some constant. Right? That's the same for every single type of wave equation. Right? From our Schrodinger wave equation, We take our wave equation, chuck it through the Hamiltonian, we should get a constant times the wave equation back. Right, so I say that this is the wave equation, but the easiest test is put this through our Schrodinger equation and see, do we get a constant times this thing back? Okay, so let's do that. Okay, and we can actually switch from doing the partial derivatives right here. So this del symbol, the partial derivative, to d, and the reason we can do that is because we're holding r constant, and so this is an equation of just one variable, and so we're actually taking the derivative as opposed to the partial derivative. In terms of how we're actually going to do it, it doesn't really matter. But yeah, these should be squared. H bar squared. I always do that.
That's my easy pronunciation.
You're gonna
I
get-
always mention that.
See, Caroline, you should be.
It's got H bar. Always
Just go
say
H bar squared.
first.
Okay. Okay, so if we're taking the derivative of this with respect to our phi, then this part here is a constant. The square root of 1 over 2 pi is a constant, so it comes out. Taking the first derivative, so we would have minus h bar squared. You didn't get it that time. I'm going to pull the 1 over 2 pi the 1/2 out. This is going to be, so after taking just one derivative, so what's in this parenthesis would be the first derivative of this. Okay, so this is essentially e raised to a constant. I is our imaginary number. M is going to be a quantized value, as we will see, but it is a constant, right? Just like they have been all the way up till now. Our only variable is really this one, right? So it's essentially e raised to the ax, which is a e to the ax. So it would be our constant I m sub l, bless you, e to the I m l phi. Okay, that's after taking the first derivative, and so these don't have squares on them, right? Because this is the first set of d over d theta. Take that second derivative, take it again. This I m l is a constant, so it can come out, minus h bar squared 2I 1 over 2 pi to the 1/2 I m l, right? And then here would be the second derivative, the derivative of e to the I m l again, which would be I m l e to the I m l phi. Okay, you see we have I m l here times I m l, so this would give h minus h bar 2 capital I should be saying that, squared, and I wasn't done yet. 1 over 2 pi to the 1/2 I squared ml squared, then e to the I m l phi. This part right, oh, all right. No, yes, I want to make it more clear that we're getting back our wave equation. So I'm going to put the I and the ml's, I squared ml squared in front, and then have I1 over 2 pi to the 1/2. right here is my wave equation. So I got my wave equation back. Everything in here is a constant, right? And so it fits. You know, it's a valid wave equation. Whether or not it works for this one, that is a different issue at this point. But at least this is a candidate, right? We can't eliminate it. What we now got to do is show that we're going to end up being single valued, or set it up such that we end up being single valued. Okay, so before we do that though, this part here, that is E, right? E to the, or E for the ML value. This I is squared, and so I squared is -1, that cancels out that. So E, the energy for a particular ML value, is equal, I squared is negative, that'll get rid of this other negative, so H R squared over 2I ML squared. Or you could have the ML, I think in the book the ML is up top here. Okay. So, the wavelength, going back to where it has to be single valued, right? In order for this here to work out, the wavelength for our wave function has to come, be equal to 2 pi r, and then, so this would get it to repeat again. But we can have multiple wavelengths within our circle, right? So if we go back to this, just looking at this figure here, right, essentially we have, let's see, this is 2 full wavelengths within this. If we were to shrink it in half, so go have 4 peaks, or 1, 2, 3, and then come back to here, as long as it returns to the same place each time, then it's good. So what that means is that n times our wavelength has to equal 2 pi r, and the reason it's 2 pi r is because we're extended out r, and so the distance that it travels is dependent on how far out it is, right? You look confused.
Say that again one more time?
Yeah, so the distance that it's traveling is dependent on how far out it is, right? So coming around here is 2 pi. Well, the distance, in order for it to go around, would be 2 pi r, how far it has to go around, and then as long as we fit a complete wavelength in there, within that spot, the wavelength could be any integer value of that. Right, so we could fit maybe 5 wavelengths in there, or 6 wavelengths in there. So if we had a really short wavelength, so long as it was essentially our wavelength has to be 2 pi r over how many repeating patterns we have, right? Move that n to the other side, right? And so what that means is that the wavelength itself has to be quantized. Only certain values of n are going to work, right? If we don't end up having a repeating pattern, then we have 2 values for a given location on the ring, right? And that doesn't work out for our wave equation.
So it kind of just needs to connect back around.
It needs to be at the same spot. So if it starts here, it needs to end up in the same spot. Right, we could have it go. Let's see if I can actually draw this freehand. Nope. Yeah. Much better drawn than that. Right, but you could have it shorter, or you could have it, like that. It just has to get back to where it was. Right, so some form of, so this would be n equals 1. What's drawn here, I think, is n equals 2. Yeah. So there's a whole bunch of different values, but the point here is that n has to equal, you could have a value of 0 that still works out. Right, so if this is 0, looks like that, it still matches up, right? So, unlike the previous ones, for this one, n can still be 0 and it'll still work. Then n could be 1, 2, ... and that will end up working out.
Would that give you a sensible answer or no?
Hmm?
0, would that give you like a sensible answer or no?
No, in this case, the answer, it actually works out. Yeah, and the reason that it doesn't violate the Heisenberg uncertainty principle, right, of knowing position is because we've actually locked the R value, and so if something's rotating, realistically, you're typically in terms of a rotor, you're talking about like two things bound together, and so the R is actually going to be changing. We're doing an oversimplification, which is why this seems to violate the Heisenberg uncertainty principle, but in a real system, R wouldn't be held constant. And so your uncertainty is going to be in your R position. Okay, so for our momentum term, right? So going back to de Broglie gave a relationship between momentum and wavelength. So momentum is equal to h over lambda, not h bar, but h. We have an equivalent for a rotating system. Instead of looking at P, we're using J. So J, if we're talking about rotating species, the J is actually typically represented as a vector coming out of the axes perpendicular to the rotation. So the figure that we had, back one, this axis here is where J would be, and then the height of that vector would be the rotational inertia. It's just how it ends up getting represented.
Wait, if you had a circular motion, right?
Mm-hmm.
And you were to find its momentum, what would it be perpendicular to where it's going?
It's the vector display of the angular momentum.
Because like, wouldn't momentum tell you where it's going?
Hmm?
Wouldn't momentum tell you where it's going, right? Or how it's going?
Yes.
It's never going in z direction if it's moving in only x and y.
No, it's okay, so to specify the rotation, you end up, if you remember back to physics, the right-hand rule, x, y, and z axes, if something is rotating from this finger to that, then the vector for the force is in the perpendicular direction.
Oh, that thought everything was.
Rotating stuff.
Okay.
Yeah, so that's why the J the way we represent J is, hold your fingers out, this is your X, that's your Y, that's your Z. If it's moving this way, then the vector is going in the vertical. So the way we would represent this is J, and then we can put a Z, because J is along the Z axis. So in your textbook, they have J sub Z being equal to plus or minus the linear momentum times R which would be equal to H R over lambda, right? Replacing the linear momentum with, by our de Broglie relationship. Oh, and then plus minus here. The plus minus tells you the direction that it's spinning, right? And that goes again to your right-hand rule. If it's spinning around, would that be counterclockwise? It's up. If it's spinning clockwise, it's down. Right? So the plus minus tells you spinning clockwise or counterclockwise. Because we're more interested, the J is the magnitude of the vector. So because it could be either up or down, we can take our rule here for our wavelength. Yeah, take this, which is our wavelength, plug it in over here for our wavelength, and then get our angular momentum in terms of stuff that doesn't have wavelength in it. Right? In terms of, well, our n value, which is quantized. So this would be equals plus or minus HR over 2 pi r over n. Our R values cancel out. You can see where we're going with this thing, right? And then this n is on the bottom. So if it's in the denominator of the denominator, you move it up to the top. So this would be equal to n h bar plus or minus we're actually going to use a different value. Instead of calling it n, so this would be where n is equal to 0, 1, 2, dot, dot, dot. Because we have this plus or minus there, that's somewhat inconvenient to keep on writing a plus or minus, right? So what we end up doing is instead of using n, we use m sub l. And that, we're going to say, is essentially equal from minus n dot, 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 0 up to plus n. I think you could also have it, I think this is how they have it in the book, ml is equal to 0, comma, plus or minus 1, comma, plus or minus 2. It means essentially the same thing. Okay, so we have our ML value here. We can plug, this is our energy. We can also do energy in terms of kinetic, right? Our kinetic energy is equal to our momentum, in this case, rotational momentum, squared over 2 pi JZ. We have our definition for JZ here, which is equals ML H bar. So we could rewrite this as ML squared H bar squared over 2 pi, which is the exact same thing that we get from here if we come about it through the wave, through the Schrodinger equation. Okay, so the whole thing matches up. Now, the other part of this, because the energy is equal to this ML value, right, and ML here is squared, if we have a negative value, we get the same as we have for a positive value. So this thing is going to end up giving doubly degenerate values, whether it's the particle is spinning clockwise or counterclockwise for all of our different ML values except 0, right, because you don't have plus or minus 0. So for everything but the 0 state, it's going to end up being, you're going to have two degenerate energies, one for the spin clockwise, one for the spin counterclockwise. Okay, now we're going to check this. All right, so first we were checking, is this possibly valid? Then we're going to check this to see if we plug in this plus the 2 pi, we should get back the exact same number. If that's the case, then this would be a valid wave equation. So, you guys have all of this? Okay, Kieran, you got this? Okay. Okay. So what we're looking for is this part here, our resulting answer to be the same as that, right? Because we're saying that this should be equal to phi theta. Okay, so we plug the theta plus 2 pi into our equation. This is equal 1 over 2 pi 1/2 E. So wherever we see theta, we're going to plug this in. So that's I ML, and then theta, or sorry, not theta, phi plus 2 pi. Now, one of the rules about exponents is when you have something added together, it's the same thing as multiplying e raised to the power. So this is the same thing as 1 over 2, 1 over 2 pi 1/2. If we distribute this out, this is IML times theta plus IML times 2 pi. So I'm actually going to do this in 2 steps. IML phi plus IML times 2 pi. This is equal to 1 over 2 pi 1/2 e to the IML phi times e to the IML 2 pi. Okay, this part here is phi of theta. Right? This here is that. Okay, so we don't need to worry about that part anymore. So we can essentially say, right, that phi of theta, or sorry, I keep saying theta, 2 pi is equal
starting disregarding the first side of phi? Because you said that first one was the wave function, right? So you said we didn't have to worry about that anymore.
Well, we don't have to worry about what's in here, we can just call it this.
Oh. Got it.
Yeah, okay, so, from Euler's formula in your textbook, there's a section called the Euler's formula. If you look in there, that's where there's the justification for e to the I pi is equal to -1. It's a very useful thing to know. It will be on the first sheet of your test. Okay, so, but this helps us out because we can actually, this multiplication is, it commutes, and so we can rearrange it, right, to get this phi e to the I pi 2ml, right? Those two are equivalent. So this part here is -1. So this is the same. 5 plus 2 okay. -1 raised to the 2ml. So ml are integer values, right? So it's either even or odd. If you take 2 times any even number or odd number, you get an even number. So we are raising -1 to an even power, which means you get back 1. So this part here is always going to be 1, and so it works out. So in terms of things that I want you guys to be able to do, right, you would be given a wave function, evaluate, is this actually a valid wave function? Given a fairly simple wave function, determine what the energy should be. So apply the Hamiltonian, this or this, right, to a particular equation and come up with what is the constant. So take the derivative of some equation. It's going to either be sines or cosines, or e to the, some power, because that's essentially how you get, your wave-like behavior, and come up with what the eigenvalue is, what the e is.
So in order for us to check if it's a valid wave function, we just literally do, psi or wave function of a variable equals wave function of variable plus 2 pi. If those two are equal to each other, it's a valid function. So basically psi of phi equals psi of phi plus 2 pi.
Oh, no, this only works for the circular, because of what we were saying is it's a repeating pattern going around the circle, and it has to be the same when it gets back to the start of the circle.
Yep.
So this is only for, it's going to be for particle on a ring, and then we'll see particle on a sphere. But a sphere is essentially, a ring, right? For other wave equations, this is the first time we've seen this, because this is the first time that this is a valid constraint. Other times, like when we're doing particle in a box, we had at x equals 0, this had to be 0, and then x equals L, it had to be 0. So this is our boundary condition. So one of the things you'll need to do is figure out what the boundary conditions are, given the description of the problem, and then first check, does this actually give, a constant? So when you plug it through the Hamiltonian, do you get a constant and the wave function back? If you don't, then it's not valid. Alright, so that's your first check. And then the second one is, does it match the boundary conditions?
So basically, you give us a function, we apply the Hamiltonian to it, which is negative h bar squared over 2n, second derivative.
Of whatever variables you're working with, whether one variable x, or x and y, or x, y, and z. Yeah?
And then we solve that, and let's say if we do get the function back and some
Mhm.
constant in the front,
Then it is a valid wave function.
Okay.
It's not necessarily the correct wave function for this problem. So first, you need it to be a valid wave function. The second is you need it to actually correspond to your boundary conditions. Right, so we could actually take, our equation for a particle in a box, that wave function, check it through, and it'll check out as being a valid wave function because it is. But it doesn't align with these boundary conditions, it aligns with a different set. And so the wave equation for particle in a box is not the same as particle on a ring because of the different boundary conditions.
and we need to know how to do partial derivatives in terms of x, y, and z, because that we don't, I don't know.
Yeah, if you can do a derivative of a single variable,
I can do that.
it's the same thing. The partial derivative just means anything like this, anything that's not x, treat as a constant.
I think it's nice.
So if you're taking the partial derivative with respect to x, then you only worry about x. Everything else treat as a constant.
There's no s in the
Hmm?
function.
Well, there's no x in this equation because by the time we got down here, we'd swapped over to polar.
Then we need to know how to go from Cartesian to polar.
No. There's a reason I didn't show you all that work.
Okay.
Is because what I'm interested in is this, and the explanation for why we were dealing with a phi, as opposed to x and y, is because it made sense for us to switch from Cartesian, which we had been using for all the systems up till now, into polar, because we're now working with something that's rotating around a central place, so polar coordinates are the most appropriate coordinates to be using. Okay.
How do we know the boundary conditions?
Huh?
Just by intuition? Like, from here, right, the boundary condition you said was like, psi of phi equals psi of phi plus 2 pi. So it has to come right back to where it was, right?
Mhm.
In a box, we know anything goes above or beyond the boundary conditions infinity, and when it touches 0.
Mhm.
We know that, but like, if you give us a problem, how would we be supposed to just know the conditions?
The reason that we've been going through all these different examples is this is not an exhaustive look at all the possible ones, but they are all permutations or variations on the ones that we've been looking at.
What does that mean?
So there's a lot of systems that rotate, right? If it rotates in 2 dimensions, you use this as your starting point, right? If they vibrate, you use a harmonic oscillator, right? So if things vibrate, the reason that we did a harmonic oscillator is because that describes things that are vibrating. You could also use this for things that look like an electron can travel in a ring. So for like a benzene ring, right? So this is also called particle on a ring. So that would be your electron stuck in the pi cloud of a benzene ring, right? Particle in a box, as we were doing with lab, was the polyenes, right? So for the polyenes, then essentially your pi cloud is your electron's able to travel that whole distance, and so it's a particle stuck in essentially a box.
What was the condition for harmonic motion? It's like, harmonic motion is basically a spring, right? It's like,
Oh, the harmonic is, so particle in a box are very steep boundaries. Harmonic oscillator is, instead of being steep, like that. So that would be your potential. So here, this is your potential. From 0 to L, your potential is 0. In this one, at, we call this one 0x, that's the positive x direction, that there is the negative x direction, right? And this is a graph of your potential.
Oh, so you would have to say psi of negative x equals psi of x. That's a condition. It has to be same. That's harmonic motion. Like if you do like the
So you'd be solving, when we were doing a harmonic oscillator, that is more having to do with the Hamiltonian. The Hamiltonian is negative h bar squared 2m. And then the derivative in how many other directions you're going, but for these we were limiting ourselves to one direction. Okay, and then plus the equation for your potential in the x direction. For the harmonic, for the particle in a box, we said that between this point and that point, it's 0. So it goes away. At the boundaries, it goes to infinity, and so you can't have a particle outside. For our harmonic oscillator, we were saying that this is
1/2 kf x squared.
that's right, 1/2 k f x squared. And so it's being modeled via a parabola.
alright, but like you see how we tested this wave function with this condition and plugging it back to the equation, and if it suffices the quality, it's a valid wave function, right? What are we testing in this equation in harmonic motion? Like if these two values of psi is equal to each other, clear is the valid function.
No, the testing the two values of psi is only for when you have the repeating motion of it coming back. Right? This is the boundary condition only for, well, particle in a ring and particle in a sphere, which we're about to do. For this one, the boundary conditions
I understand it.
were that psi is 0 here and here. For this one here, we were essentially adjusting what the Hamiltonian was and plugging our wave equation through this, and we should get back a constant time to e. So that would be how you check, is you need to get a constant time to e. But for this one, your wave equation changed depending on your n value, right? And that was the Hermite polynomials, which don't try to memorize. They're going to be given if you need them.
Okay.
They probably won't be on the first sheet because they take up a lot of space. So if you need them in a problem, they will be given. Okay? Okay. So, the last one of these particles in a X, Y, or Z type thing. Okay, particle in a sphere. Okay. Oh, and the lecture notes are now complete and they've been uploaded. So the finalized ones for chapter 7, they're on there, but it's broken up into the 2 sets, just because otherwise it's way too many. Okay, so we will be starting in sort of a similar fashion to what we just did. Right? Except, instead of just being 2, a sphere takes up 3 dimensions. Okay? But the way we can think about a sphere is actually a whole bunch of rings. Right? So, how we're going to view this, and we're going to see my drawing skills. I just failed. That's supposed to be a sphere. So essentially we can think of this as being a circle or a bunch of rings. Right? Stacked one on top of the other. So we have two different variables for how we're going to be rotating things. It makes sense, just like we did before, to move from Cartesian coordinates to polar coordinates. For the particle on a sphere, we're again going to be saying that the radius is constant, and it's just going to be the particle sitting on the outside of the sphere, right? That reduces us right away from 3 variables to 2. Then, what I'm going to say is conceptually, we're going to think about this as our particle on a ring, and we just stack a whole bunch of rings to make the spherical shape. So we're going to be going around our circles, our rings, right? And the angle that we use to go around is again going to be our phi. We also need something to designate where we're starting our ring out at. And so if we call this the center, the angle no, not that angle. That angle there, we're going to call that theta. So going from here up to say where we're starting the ring out. For this one though, for our phi here, this ranges from 0 all the way up to 2 pi, right? It goes all the way around a circle. For this one here, in order to draw all of the circles that we need, you start at the top, and all we need to do is go down to the bottom. If we come back around, you're drawing the circles twice, right? So our theta is going to range from 0 just to pi. If we go to 2 pi, then we're making twice the number of rings that we need, right? We're duplicating the rings on the run back up. Everyone okay with that so far? Roy, you look dubious.
How do you make two rings if you go all the way around?
So let's say we were following it coming down. So make a ring here. So I'm going to go da 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 down. So as it's here, I make this ring. It moves to here, I make this ring, there, this ring,
Oh.
all the way down. Right, and so once I do this last bottom ring here, that's as it's gone from, oh, sorry, that is theta. So as it goes from 0 all the way down to pi here, we've made all of our rings. If I now go to here and make essentially this ring, I already made the ring when I was over here. Right.
Well, I thought you were doing like 2 sets of rings, one's going around, and then one's going like vertically like this.
Oh, no.
Okay. That's what I'm saying.
No, it's, we have to essentially map out the surface of the sphere. And so if we have a ring that we make here like this, and we make another one that's touching it, right, we eventually fill this in, right, and we fill in the whole surface of the sphere. But we only need to go from the top down to the bottom. If we go back up, then we're giving it a second coating and having twice the actual surface area, right?
Yeah.
Okay. So that's how we're going to be thinking about. Now, because of that, as it's going around the ring, we're essentially doing each one of those little wedges that we did is essentially a particle on a ring, right? So we should expect to see in this equation particle and ring somewhere fall out of it. Right, so our expression for as is going around this way, right, should give us particle and a ring, and then we get an additional component. Okay, so we're doing this part here, which would be the partial derivative in 3 directions. Right, so our Hamiltonian is negative h bar squared over 2m partial second derivative x second derivative with respect to y and with respect to z. If you remember back from when we were doing particle in a box, there was a shorthand notation so that we didn't have to write all that stuff out, and that was essentially 1 squared 2m. What's in here, we can represent that with an upside down delta, which is called a nabla, or nabla, N-A-B-L-A, squared. This thing here, without the square, just means take the derivative with respect to x, y, z. If we square it, it's second derivative x, y, z. Okay, it's something that you'll find as you're scoping out the internet for doing this. So this is in Cartesian coordinates. Swapping over to polar coordinates, again, I'm not interested in you guys being able to derive or do the actual switch, although you can. It's not something I'm going to be asking for. Switching this from polar to Cartesian, so this is all the R terms. This other term here is the Legendrian. It's sort of the equivalent to the Nambla, except for when we're going around angles. This here is, and the reason that we're using this, or this gets used a lot, is, well, I guess you'll see when we write out the whole thing. Squared plus 1 over 9 theta. Yeah, this here is the Legendrian. Okay, so we can see that it's broken up. What goes before the Legendrian is just R values, right? So if we say that R is being held constant, if del R or dr is equal to 0, then this thing here is 0, that thing there is 0, so that all goes away. And then all we're, well, quote, all we're left with is a bunch of psi's and phi's, and then a constant out front. Okay, so we've taken something that was in 3 dimensions, and we've cut it down to 2. And it's in polar coordinates, and we're going around a sphere, and so using polar coordinates for a sphere ends up working out a whole heck of a lot better. So, what this ends up giving us our delta squared, if we're saying that r is being held constant, this is essentially 0 plus 0 plus 1 over r squared, like that. So our Hamiltonian, this part here, right, our Schrodinger equation becomes minus h bar squared over 2m 1 over r squared Legendrian squared. We swapped from x, y, z to polar coordinates. So this would be, how do I want to do it? 5 theta? Yeah. Oh. Now, the question is, do you notice anything about what's on the left-hand side? So something we did when we were looking at,
MR squared.
hmm?
MR squared.
Yep, mr squared. So that was I. So we can write this as minus h bar squared over 2 capital I Legendrian squared like that. Right, and that gives us a little bit of confidence that we're doing the right thing because that is the angular momentum, right, which has to do with spheres and rings and stuff, and that's what we're trying to talk about. And so the fact that this falls out of it gives us some confidence that what we're doing is actually starting to work. Okay. Okay, now, one of the things that your book and a lot of sources do, and so I just want to have you be aware of what's going on, is they lump together this stuff here with the E to have, rearrange the equation just a little bit. We're going to let that equal, what is it, E, yeah, 2I E over h bar squared. So essentially it's taking this stuff here without the minus sign, moving it all to the other side, so that this then would have our equation be minus Legendrian squared theta phi equal that is another type of expression. Sometimes the negative is going to be on the other side. So sometimes you'll end up seeing it like this, just depending on where you're looking. Okay. Now, one of the things we have been doing on some of these systems, we did it when we were talking about particle in a box, is when we have a system that has 2 or more variables, we can do a separation of variables by saying that our equation here, we can represent this by 2 other equations multiplied together, and then try to treat them individually to simplify things. So we can say, or we can try, saying this And the common way of doing that is take whatever your variables are, use the capital representation for the functions of the variables themselves. Yes?
Where did the 1 over r squared go into like that? Can you change?
So MR squared is I.
This part here, yeah. We use, just like we did before, mr squared is I.
Oh, yeah, yeah.
Yeah. Okay. Okay, so what we're gonna do is we're gonna take this, plug it into, well, let's see, this one here, using the Legendrian in this form. So we see all the gory detail of it.
Do we need to know this?
Hmm?
You need to know this, right? The derivation you're doing right now?
Not per se, but we're going to be using things like this coming up when we're doing coming up with the hydrogen atom. This particular trick is a good one to know. So, we're going to write out this being applied to that. Okay, when you're doing these, when you're doing this one, keep in mind, yes.
W squared, so the Legendrian.
Yep. Bonus points. Okay, so when we're applying, something with a hat means that it's an operator. Remember that the operator applies to the thing to the right of it. So if we're doing this as an operator, we're going to use this as an operation and then plus this operating on our function over here. Right? We're not going to put it next to all of our derivatives. It only gets put at the end of a series of processes. So this will give us 1 over sine theta squared. Yeah. Partial derivative of phi squared plus okay. Now the thing about the partial derivatives is when you're taking the partial derivative of something, anything else gets treated as a constant, right? So it can move outside of our derivative sign. The left-hand side here, right? We're taking the partial derivative with respect to phi, so our theta equation, which has no phi's in it, gets treated as a constant, so it can move outside. Over here, right, this is going to be taking with respect to theta, that's with respect to theta, so none of this derivative stuff has to do with phi. So you can take this phi, move it to the outside. So that gives us theta of theta over sine squared theta Okay, now if you look, well, so this whole thing is our Hamiltonian times our wave function, right? We don't have this h bar, we don't have this in front of it. In fact, what we're looking at is essentially this equation right here, right? We took our Legendrian, applied it, our Legendrian operator, applied it to our wave equation. So that should be equal, to minus the stuff here, this value that has essentially our E lumped in there with all the other constants. Like that. All right, and so this is essentially is related to our E times, and this is our wave equation. Right, we said down here, our wave equation is equal to that. So that's what we got. Okay? I'm going to do two steps at once. I'm going to divide both sides by this, right, to get my E term all by itself. And then I'm also going to multiply by sine squared, because we got a bunch of sines all over the place. All right, so if I multiply by sine squared, I can get rid of this sine squared, and I only have one sine in one spot. So I'm going to, if I divide both sides by this, and multiply by sine squared on both sides, that will give me 1 over plus sine theta over okay, so why the heck did I do that? If you look at our equation now, this is only in terms of phi. All right, so we can, and we actually just saw this earlier today. While it might not look like it, this is essentially our particle in a ring equation. This part here, we will deal with that in a bit. Okay? But this whole thing here is just thetas. Right? There's no phi's in there. And so we can treat this as a function of just theta. This is a function of just phi, which, while it looks complicated, because we're adding the two together, we can treat them separately and then bring them together when we're all done. So it actually makes things easier. Okay? Okay, so this part here, we already worked out. That was our wave equation from before, from before, we were treating it as d phi squared of our wave equation. So this here is our wave equation in the phi direction. This was equal to minus ml squared times our wave equation. All right, this is from particle in a ring. This is what we just did.
D squared d theta d plus d squared d phi theta or d phi squared. It's your second derivative, right? know, that's the
Oh. Squared up top. Yeah. Okay. So we already know what this is. Alright, if you look here, this is essentially taking this equation and dividing both sides by our wave equation. So what that tells us is that this part here should end up being minus ml squared. We divide both sides by phi of phi, comes over to this side, and is 1 over phi of phi, which is what we have here. When we were doing our particle in a sphere, we got that the second derivative of our wave equation was equal to our constant times our wave equation, which was our ml value. Okay, so this whole thing here should be minus ml squared. Which means that this, we can rearrange it to get sine theta, theta of theta, del over del theta, sine theta, del. We take that plus sine squared of theta. So this part here is minus ml squared. I moved this to the other side, so this should be equal to 0. So that means the only way we have a constant, we have a whole slew of stuff in terms of theta. The only way for this to equal 0 at all times is if this whole thing here is plus ml theta. Okay. That doesn't actually help us figure out what the wave equations are, but it gives us an idea of a condition for this that we're going to use later. This value here, the wave equation for this part, is going to be the same wave equation that we were using for particle and ring. Right? And the reason it's the same is because this is the same as the particle and ring that we had just a little while ago. So, we've already worked out that this is going to be, theta of theta. That will be approximately equal E I M L phi in an unnormalized form. The reason that it's approximate is whenever we're dealing with wave functions, we try to normalize them first, right? And in the case of the particle and ring, it was 1 over 2m quantity square rooted, right, was the normalization constant. So the key part here is that this ends up being an exponential. Okay. So now that we we have an idea of this, we're actually gonna go back a couple steps and look at, we're gonna change our representation for this to being equal we're gonna change the variable that we're using, and the reason we're doing that is to be consistent with the book. Right, so the y value here, or this y equation, these are called your spherical harmonics. So, taking essentially our equation that we have up here, or I guess plugging this into our Legendrian. Okay, so for that particular equation, there are known solutions. Every time, r squared
That's the only place this class.
is r squared. Okay. So, similar to when we were doing a harmonic oscillator, right? How the values changed depending on, or the equation for the wave function changed with each one of the different n values that we selected. Unfortunately, for this particular equation, the solutions also change with a particular set of quantum numbers that we select. So it changes with the ML value, our magnetic quantum number, as well as another one, L, which is our angular momentum quantum number. So the reason that we're using the Y here is because we're specifying it in terms of two quantum numbers. Right, so this is essentially our wave equation, but we have to look up each one of these values, the ML value and the corresponding L value, to find our equation for the spherical harmonic. Right, so similar to how we, for the harmonic oscillator, right, how we have the Hermite polynomials, we have the same sort of a thing for our spherical for our particle on a sphere. The equations are called the spherical harmonics, right? You will not need to memorize these. Instead, you need to know how to use the table. So, if we had, if I said ML equals 0 and L equals 1. You look here, L equal to 1, ML equals 0. that would be your wave equation, right? 3/4 pi square rooted cosine of theta. You plug that in here. And ta-da, that would be your solution.
Oh, man.
Just like that.
Okay, the thing here though, and it might remind you of some general chemistry stuff. Your L value goes 0, 1, 2, 3, 4 by integers. ML value, right, goes from negative L to positive L. We're starting to see where these are coming from. It will make more sense once we actually hit the hydrogen atom and apply this instead of a particle on a sphere to actually looking at the orbitals. But essentially, that's what we end up with. The energy for any one of these particular orbitals, or sorry, not orbitals yet, for any one of these particles on a sphere is going to be L times L plus 1 quantity h bar squared over 2I.
Just copying notes at this point.
Okay. Oh no, that's not quite it. We will be taking a break.